Hello everyone. Hello, hello. We're ready to start. What did we see last week? Optimal power flow, true, that's the whole topic. But more specifically, we saw a number of things, but in particular, affine control, a method for defining a control policy, which is linear affine, linear plus constant. What we will see today is another techniques, an alternative to this, which might use optimization problems that are bigger in size, so they're not always applicable, but that is very powerful. It's called model predictive control. I'm sure you've heard of it or perhaps even had to do with it already. So model predictive control is really a technique of choice, which is very, very frequently used in the context of controlling an energy system and in particular a smart grid. The good news is that it's very simple. So we will see what it is. So the idea is to have a receding horizon and otherwise to simply solve an optimization problem. It will obtain a policy, but the policy is the result of solving the optimization problem. We don't know the form of it, unlike in what we saw last week. Last week we posit the form, a linear form for the control policy, and we compute the optimal parameters of the policy. Here we will not know what the form of the policy is, and that's the magic and the power of this technique. In particular, in most cases, it doesn't give linear policy. It will give policies that are much more sophisticated. What's the difference between a policy and action? That's a term, those are two terms that are very frequently used in this context. We saw that last week. An action in the context of OPF, optimal power flow control, is which value we assign to generators, for example. That's the action we take. That's the vocabulary that is used in this context of control theory. A policy is a method to derive an action based on the state that is observed of the system, or the past history, or whatever we have observed. So a policy is more general than an action. And we saw last week that when we apply to the OPF problem, when we apply a linear policy instead of a static computation of a robust action, we have something much better that works better in the sense it's able to handle a much larger uncertainty and also provides a smaller cost. So how does MPC work? Well, it requires something like this, an equation that gives the dynamic of the system as a function of the current state, the actions that we take now, and the disturbance. So that's familiar, that's the framework we had last week. But we need this equation to be known in some form, exact or approximate. This equation is known as a dynamic system. In discrete time, a dynamic system is given in this form. In continuous time, it would be an ordinary differential equation, but most of the time in our context, we will use discrete time systems. So we have state that we can observe or estimate. We have the control, that's the decision we have to do. And we have the disturbance, that's nature or uncontrolled things that play against or with us, we don't know. We need this model, that's why it's called model predictive control. We need a model. Unlike other systems of learning systems that are model-less, where we have a black box, for example, a neural network will try to learn what is the result of an action. Here, we do need a model. But having a model is usually something that's quite, makes a lot of sense in our setting because we know at least the physics of a system and we can very often estimate the parameters of the model. Given this, how does it work? We do repeatedly, so time is discrete. At every time, we observe the state x, xt, and we choose one control action. How we will choose it, we will discuss in a minute. Then nature plays and adds a disturbance to the system. And the result of the current state, the action that we took, and the disturbance is a new state, x of t plus 1. And then we assume that as a result of all this, we have to pay a cost. The cost is a function of the new state in which we are and of the control action we took. The control action has a cost that we're familiar with that. For example, if we decide to put a set point generator to high, that will cost something if the generator is using some fuel. And there is a cost associated with the new state, which may be, for example, if we're doing voltage control, we care about voltage control, then we will have a penalty which is large if the new state has a voltage that deviates a lot from the nominal values. Those are examples in our setting. And how this works is we will try to minimize, so in the way we will compute UT is by minimizing the integral cost over some long period. This long period is called the horizon here. We'll do an example, not for a grid, but for another type of energy system, which is related to the topic of today, which is demand response, which is how we should optimally use the fact that electricity comes with a variable price, which is not very frequent today, exists in some countries, is enabled by smart meters. But the idea for controlling the grid in a very distributed and efficient way is to expose to customers the fact that electricity is more difficult to obtain at some periods of the day, for example. Even in winter, there is sunshine most days around noon. So in a not so distant future where there's a lot of solar energy everywhere, then the price of electricity, a lot of electricity is available around noon, at noon time, around the middle of the day. So we would like to incentivize people to use electricity at this time rather than at another time of the day when there is less energy. That's an example motivated by solar energy. That's overwhelming. But there are also other reasons, like wind energy also is variable. So there might be a lot of wind now, because on the North Sea, the wind is blowing hard, and then energy becomes cheap. So this triggers variable, or one method to pass this information to customers is to make prices of electricity variable. Of course, that assumes that the consumers can adapt. And one way of adapting is to do exactly what we're doing here, compute an optimal use of the cost of electricity for heating our house. In order to do this, we need a model of the house. So this is a well-known thing that can be found in all details, for example, in this book, David McKay, Renewable Energy Without the Hot Air. That's a book of a bit more than 10 years ago. David McKay unfortunately passed away a few years ago. So he was an advocate of renewable energy in the UK and everywhere in Europe. And he wrote a very, very useful book. He's a physicist by profession. And this book has all the numbers that you need to do renewable energy. I mean, how many wind mills do you need over the whole United Kingdom if you want to be realistic about living on renewable energy with wind, for example, and solar, etc. So he gives all the values. He doesn't give a solution. He gives all the numbers that we need to do such evaluation. So, for example, we will model in this course David's house, which is this one here, which can be modeled in this way. So if I buy, so it's heated by a heat pump. So a heat pump has a coefficient of efficiency, which transforms the electricity into heat. And the interest of a heat pump is that this coefficient of efficiency is larger than 1, much larger than 1 if it's a heat pump with a deep ground system. Then for such a case, the coefficient of efficiency can be 4 or 5. If it's an air heat pump, the coefficient of efficiency is probably around 2. And if this is resistive heating, if you simply have radiators that burn the electricity in a resistance, the coefficient of efficiency is almost 1. It's close to 1. So this is how much heat we put into the house during an interval of time dt. So U of t is the energy that we imported. That's the one we will pay for, multiplied by the coefficient of efficiency. Now what happens to the energy we put into the house? Some of it, hopefully most of it, is used to heat the house. So capital T is the temperature of the house at time little t. So in this simplified model, there is only one temperature. It is simplified in the sense that there is only one temperature. In a more realistic model, the temperature is not uniform everywhere in a house. We would need multi-dimensional model, but we won't do this. That makes it complicated and improves a bit the accuracy, but not much. So most of the energy we use, we hope, goes into increasing the temperature of the house. So that's this coefficient here, CDT, and the coefficient is called the inertia of the building. You have a building that has big, thick stone walls, then you need a lot of energy to heat up, to increase the temperature, because you need to heat up all those big stone walls, big stones, right? So you need a lot of energy to increase the temperature. So that's the inertia. The other thing is the leakiness. Part of the house is not perfectly insulated, so part of the heat that we put into the house goes out. In fact, even if we don't put heat, if the house is at a higher temperature than the outside, it radiates some of its internal energy that goes out into the outside. This is captured here by this coefficient of leakiness, which in this model is equal to the difference between the temperatures here, the inside and outside temperature, multiplied by the coefficient of leakiness. This coefficient is small if the house is well insulated, and is large if the house is poorly insulated. So we have the numbers for my case house. Those are the numbers here. That's the ground heat pump with not so large efficiency, but decent efficiency. So that's the first thing. We need such a model. Then how does the MPC work? Well, we discretize this model, which is the physicists give us this model, which is in continuous time. We make a second approximation by making it discrete time. At the time scale that we're speaking of, the temperature of a house, it's very easy to discretize, right? We're not modeling the temperature inside a living cell, for example, where there can be large gradients at a microscopic scale. Here we are at a macroscopic scale in terms of temperature, so temperature doesn't change significantly within seconds or even minutes. So the discretization is very accurate. So if we discretize, then we replace dt by delta t and the derivative by difference. And so if we take, for example, 1 minute time scale, which is largely sufficient for that type of thermal systems, then we obtain this equation here. So that's the energy that we put during a time delta t. So that's the power times delta t, that's the energy. That goes into here, heating the house. Sorry, that's the inertia part. So it goes into changing the temperature, but it also goes partly into the outside here. Now, if I number crunch all this and split the variables differently, I have exactly the equation I wanted, which says the state of my house, which is the temperature. That's what I'm interested in. The goal of heating is to control the temperature. The goal of the OPF was to control, for example, voltage or power balance. Here, the goal of heating is to control the temperature. Then we see that it's a linear function of the current temperature. The next temperature is the linear function of the current temperature, of the energy we put, or the power that we, at time t, time and a linear component of the outside temperature, which is now a disturbance here. So we have a state, the inside temperature, a control, how much we decide every minute to put what's the set point we give to the heat pump. And the disturbance is the outside temperature. If all of a sudden it becomes very cold, then there will be more leakiness and more will go out. It's a very simple model. I'm not taking into account two other factors that are typically taken into account in such models, which are the wind and the solar irradiation. So in reality, the house might warm up for free because there is some sunshine that goes through the window. So that would be another term into the equation here. And the leakiness might depend also on the wind. If there's a lot of wind, then particularly in British houses where the windows are not so closing so well, then the loss of temperature might be larger. So I ignore all of this here. It's on a gray and non-windy day, if you want. So that's our state model here. Now, what is the cost? Well, the cost is how much we pay here. That's this function here. So every minute we pay here for the power we put into the heat pump. Plus here we would like to control the temperature. So there are two ways we could do it. We could put constraints by saying we want to force the temperature to be within the desired band, which is here between Tmin and Tmax. A simpler way to put this is to put what we call a soft constraint by using a penalty function. That is a function of this kind that says as long as the temperature is within the acceptable band, there is zero penalty. If it's too large or too low, there is a penalty. There's a penalty if it's too large because we're wasting money by heating too much. And there's a penalty if it's too low because it's cold and we don't want to be cold. And the goal of the heat pump is to prevent this from happening. So that is how we put it. Very often when we do model predictive control, we will have large linear programs to solve. And if we put hard constraints, they may be unsolvable, or solving them with a lot of constraints may make the problem very difficult. So instead of that, we often put what is called soft constraint in this form, which is justified a posteriori by the fact that the program will be easier to solve here. It's also justifiable in this case here because this is really a soft constraint. If we vary a little bit here, if we go a bit below here, there is no big damage done to the system. So it's not like a hard constraint that we have, for example, when we have a generator that has a maximum speed. If it goes above a certain speed, you might have damage. Here, it's not the case. So it's really acceptable to have a soft constraint. But typically, we will take a penalty, the price of the penalty here, that will be very large to make sure that in de facto, it acts as if we had a hard constraint. That's the standard technique. So this is how the model is posed, but now back to MPC, which is the heart of the topic today. How does MPC work? Well, it does the following. We do repeatedly. So every minute, we will need to run an optimization problem and solve it. That's the price to pay. If you compare to affine feedback policy, we computed the affine feedback policy ahead of time. Then we have the parameters. Once the parameters are put in place, implementing the policy is obvious and trivial. It takes a fraction of a millisecond. It takes just a few computations on your microprocessor, or you can even do it on smaller systems that don't even have microprocessors. You just do multiplications and additions to implement the policy. So it's very easy to implement the policy. It can be implemented on extremely dumb devices. MPC requires to solve at every time step an optimization problem. So it requires a Raspberry Pi or a National Instruments box or whatever. It requires a full-fledged computer to be involved in the loop. That's the price to pay. So we observe every minute the state, and then we do all this exercise. We must have a prediction of the disturbance. H is the horizon. In our example, it would be 2 days. So we want a horizon that's long enough so that it incorporates the benefit of doing things in advance. So if the horizon is too small, then the benefit of MPC will not show up. It's not interesting to do an MPC. What is the benefit of doing things in advance? What can it be in the context that I gave here? Can you imagine why we would be interested in doing something now by looking ahead what might happen in the future? Yes? Yes, and specifically? Well, if at a period of time the cost of electricity is very low, then we want to heat now at this time when the cost of electricity is very low. But how much do we need to heat up? How we will increase the temperature? By how much do we increase the temperature? This we need to compute. There might be times also where we do need to heat because the temperature is dropping and we have a choice to do. Should we heat now because temperature is dropping a bit, or should we wait a bit and heat in 5 minutes when the electricity will be much cheaper? So those are the things that we may need to take into account. So we want to have a look at the future, at the entire trajectory, and decide what to do now by having a prediction of the future. So that's another thing we need for MPC. This form of MPC is called certainty equivalent MPC. Certainty because we obtain a prediction. There are other MPCs like scenario MPCs where instead of having a prediction, a point prediction, we have a set of scenarios. We have a number of predictions with probabilities attached to them. It's not very complicated, but we will only look at this in detail in this course. So we obtain a prediction of the disturbance. In our case, the disturbance is what? Is the temperature. So it's fairly easy to obtain at least a coarse prediction of the temperature in short term. You can be based on past time series or ask an online service for that, or you can simply use very, very coarse predictions. I mean, if you're in January or in July, then of course the temperatures are likely to be different. The good thing about MPC is that we don't need this prediction to be very accurate, but we need still to have some idea. So we predict the outside temperature over the next 48 hours, for example. And then we solve an optimization problem that has as control variables all the set of temperature of power set points over this entire horizon. So we pretend we decide now what are all the decisions we will take over this entire horizon. Assuming the unknown things of the future are as we forecasted them. In this example, I'm assuming I know the prices of electricity when I do this exercise, which is typically the case in variable prices. We tend to know them 1 or 2 days ahead of time so that systems can adapt and do exactly this. So we solve here a big optimization problem that returns the sequence of actions, and we implement only the first action, the one we need to do now. So we implement this action. Then we do again, we wait for one time step. In the meantime, the disturbance will be revealed to us. So the true value of the outside temperature, or in other cases, the true value of whatever disturbance will have an effect. And we measure. So if the model is exactly correct, then xt plus 1 will be equal to that. We will measure xt plus 1, and then we go back to the first step, and we do it forever. Here's an illustration of how MPC is used for autonomous car, for example. Well, autonomous car driving does an MPC by controlling now the control power. The control is the power, the torque on the wheels, on the directions, the angles of the wheels. Do we brake or do we accelerate, and how do we turn the wheels? So there's all the control decision we need to take. The forecast is based on cameras that watch the trajectory here, that observe the trajectory. So we have to be on this road. We can easily compute that the optimal trajectory given a forecast. So a forecast is that the disturbance will be that there's no disturbance, for example, if there's no car coming in the other direction here. So we compute a set of set points we will need to take that will lead to this trajectory, the green one. That's the one that's computed at time t. Then we implement all the actions that lead to that, and then we are at time t plus 1. We're not exactly where we had forecasted because there's always errors in the disturbance always plays a role. In our example, the disturbance is just the outside model because the outside temperature. The model is fairly accurate. In other cases, like here when you're driving a car, the model itself is not very accurate because it's hard to predict everything, in particular the shape of the roads, the adherence of the wheels, etc. So it's an approximate model. So the disturbance comes as additional noise added into the state equation. So one way to model a system that's not very accurate is to include a noise term here. So the noise will come and play a role, and we will be here. So in a car, this is done at the time scale of millisecond. So 1 or 2 milliseconds later, we measure that we are here, and then we do it again, and we compute, and we go here. So that's how MPC works. We call it receding horizon control techniques because we have in mind a certain horizon over which we control things, and this horizon moves as we move forward. Question?
So in MPC, if we're predicting a sequence of actions all the time, why not simply learn a policy initially that would like be optimal for a sequence of like with a sort of reward that takes into account future states, so that when you have learned it, all you need to do is take one state and then predict the next action and so on, rather than always having to solve this like long horizon optimization problem. Wouldn't that be like heavier?
Yeah, so the question is why not learn a policy instead of doing it on the fly? So that's another technique. We've done this last week. Last week, we had a system that learns a policy. We posit that the policy is linear, and then we learn what are the optimal parameters, the set of coefficients of this. Now, in a state like this, it probably is done also with linear policies here. Then we can learn this, and that is much more efficient in real time. In practice, for many systems, linear policies are not always very good, because when we look at the details of what something like MPC does, for example, we will see that it's very nonlinear. It's most of the time threshold-based. If something is larger than something, then go in this direction, otherwise stay where you are. So there are big discontinuities that make linear policies non-efficient. But of course, there are non-linear policies that you could learn. That's another topic, and it would be an entire course. It's the topic of reinforcement learning, where we use what is called a Markov decision process that will model every. So we assume the model. We still start assuming that the model exists, and we want to learn the policy. Markov decision processes have the problem that the state of a policy is huge, because a policy has to decide in advance for every possible value of the state x, what is the probability distribution of the actions? Which action will you take with which probability? In a simple scenario where x takes 10 possible values, then you can do it. But if x is a continuous variable, like the torque, the speed, the position, etc., if it has, or in a smart grid, if you have a distribution grid with 100 buses, 3-phase, 6 complex parameters per, or three depending, at least 3 to 6 complex parameters. So you have hundreds of dimensions, and it's continuous. So the state space becomes huge, so that those theoretical things with Markov decision MDP, Markov decision processes, they are not applicable to large systems. So what can be done instead is to use artificial intelligence learning techniques. Instead of having a big table that says for each value of my state, what is the action I will take with which probability, you do like ChatGPT, you train a neural network that will approximate this. And you hope you can train it on zillions of examples. That's an alternative.
And can we do that for?
Yes. Yes, we could, but that's a project of a completely different scale, right? You will need a mega supercomputer that you will train on zillions of grids or that you simulate, etc. And at the end, you will have a big neural network that will be a replacement for that. But this big neural network, you will need to retrain it whenever you change something to your grid. That's an alternative, and I think there will be interesting projects to do in the future in this direction. Yes?
Is it correct to say that the more accurate the model is, the more points in the future we would predict? Because it would be less.
Is it correct to say that the more accurate the model is, the more points we'll have in the future? In theory, yes, but in practice, there are even 100% accurate model can lead to such systems that are, when they are nonlinear, I'm sure you're familiar with the principle of chaotic system. the fact that there could be the weather system is known to be a chaotic system, where the model for the weather system is accurate. It's given by the laws of physics, 100% accurate. But there can be a small change somewhere on the Atlantic or in Australia, a small change in weather, in wind speed and temperature that might result 3 days later in a completely different prediction value than what was predicted. Those are called chaotic systems. So chaotic systems are systems that are perfectly deterministic. The model is perfectly well known, but a small change in the initial value might lead over, not instantly, but over a time that is not too large, into radically different trajectories. That exists in many systems. And I'm sure for this happens also. So there might be, it's probably not useful to imagine that you will have a perfect prediction of what happens over longer term. But that's a good question. The accuracy of the model is part of the problem. But even a 100% accurate model will not solve everything. That's the paradox of a nonlinear system theory. So back to our much easier system here. Since we have a fairly accurate model of the house, this is easy to have because we're just modeling a house and not the universe or the weather in all continental Europe, we can solve the problem, and that gives exactly this. So I take a horizon. My disturbance is the outside temperature, so I predict it. And I have to minimize the integral costs of all the actions and the penalties over the horizon, subject to the state equation, which is saying that whatever I do at time s leads to a change of state at time s plus 1, and whatever nature will do will lead into this, which I predict to be that. And also I have constraints, hard constraints on what I can use on my controls. They have to be within some bounds here. So this is my model here. So observe that at every time t, we need to observe the house temperature. So we need a thermometer, at least in this system here. We need to compute the next actions by solving the optimization problem, but we implement only the first of the next actions here. Only ut is used. Ut plus 1, etc. are dropped. They are computed, but they are forgotten. Hopefully, if the system is not too chaotic, the new ut plus 1 that will be computed will not be very far from ut, but that will be a bit different. And it is the interest of MPC that MPC automatically adapts to noise and errors in the model, because at time t plus 1, we will start from the observed state xt plus 1, not from the thing predicted. So there is this automatic adaptation here. So I implemented this for this house with temperature, outside temperature, which are the blue dotted line here. And the temperature forecasts are these nice sinusoid here. So you see those are forecasts from historical time series, not very particularly smart here. There are two y-axes, the orange and the blue. So the orange are the price here. Those are the prices of electricity. We see that they are low at night, more expensive in the morning peak, medium value during the day, with a low value around lunch, and another high value in the evening peak, and again low at night here, which is one possible example of how electricity prices are influenced by renewable energies. In blue, I'm showing here the temperature band. So here, this is a fairly comfortable band between 19 degrees and 21. So the minimum temperature we accept is 19, and we don't want to go above 21. So we accept here a dead band. If we don't have a dead band, there is not much you can do. If you want the temperature to be exactly 19 degrees, then as soon as it deviates a bit, you need to heat, and you stop heating as soon as you sense a measurable difference between 19 and what you measure. That's what a thermostat is doing. The thermostat is having, in practice, still has a dead band, but a minuscule dead band, it keeps the temperature almost constant, equal to 19 degrees, for example. Here, I'm allowing some variability. That's the, this is modeled by our penalty function. We see that the control was perfect in the sense that even though it's a soft penalty, the temperature was always within the deadband. This is because I put a very high penalty value to being outside the deadband. We can observe here what the desired behavior. We see that at night we were at 19 degrees, and towards the end of the night we start heating up to 21 degrees. And why do we do that? Well, because we know that very soon electricity will be very expensive. So we are at 19 degrees, so the temperature will drop if we do nothing, and we will need to heat at this time when electricity is very expensive. So, and we see that we don't heat. So when we see this exponential, negative exponential curve, it simply means we're not heating. The heat pump is not working, which is exactly the desired behavior. We're not heating here during the peak hour. And here again, during the second peak hour, we're also not heating. And here we see that we may need to heat even at the time a bit before electricity is expensive, and here the same time. And the true, so we see the temperature oscillates, and we see that it is doing what it is intended for. So it is truly anticipating when the temperature will drop and electricity will be cheap, and this is when it will use the energy to heat the room. That's the cost we have here. We can compare to the thermostatic control, the one that keeps, so to be fair, we put it at the lowest value of the deadband at 19 degrees. So we put the thermostat at 19 degrees, so it's always heating. Of course, the thermostat must have also a minuscule deadband, so when it's between 19 and 19.1, or whatever the accuracy of the thermostat is. So as soon as it senses that the temperature is getting below, it heats, and when it senses that it is getting above 19, it stops heating. So that's what the thermostatic control would be doing. And we see that the main difference is, well, the temperature is constant, which is a benefit for comfort, but the cost is considerably larger in this example here. And in particular, because it is heating also at the periods of very high cost. Voilà, so that's the story of MPCs. Now, before applying this to our voltage control problem that we will have in the lab, for example, we are systematically confronted with translating an optimization problem like the MPC into something that optimization theories can handle. So we have to do a number of things. We've started doing some last weeks, like removal of the max and transformation of things to make them linear. So we have systematically this problem that is not taken care of by typical software packages. So we need to be aware of it and do something of it. In particular, when we have the penalty function, we will have nonlinear functions that occur everywhere, and we will need to be able to handle them well. So let's do a little drill on the max and min. Here is a small drill on combinations of min and max here. I have a function of two variables, x and y, that are independent in the sense they live in a space x and a space y. I can do several things. I can take the max, I can maximize with respect to y, and so the result of this depends on x. And then I take the minimum with respect to x, and I can reverse the order. What happens if I do that? That's the question of this quiz. I close the poll in a few seconds. Closing. The majority says B, but the majority is not even right, even in Switzerland. The correct answer is, whoops, is C. And it's an important thing to realize, to understand how, let me use an analogy with mice and elephants. Mice are small, elephants are big. Even the biggest mouse is smaller than the smallest elephant. So let's assume this, right? Now, assume I have on the chessboard, I have mice and elephants. And my x is the x coordinate, y is the y coordinate, and f of xy is the mass or the volume or whatever of the animal that's at this coordinate. That's x, f of x and y. So if I take the min of f of x, y for a given value of y that I call x1, it means I fix y, I fix y to be y1 here, and I look at the minimum when I fix the y coordinate over all values of x. Then it's a mouse here. I must say, I also put another constraint. It's like a Sudoku in my example here. I put a constraint on my chessboard that there is always an animal of every type on every row and every column. There's always an elephant or a mouse and a mouse on every row and every column. So if you think of this chessboard, then you will remember for the rest of your life the correct results of this quiz. So here I'm taking the minimum of x of xy for y is y1, and it's the weight of this mouse here. I do it for every row. I have all the means here. And then I take, so this is what I'm doing here for B. I'm computing B star. And then I take the max of all of those quantities, and that gives me B star. Right, so it's a mouse. If I do the opposite, if I compute A star, I fix x to x1, and I have the smallest elephant on this column, the largest elephant on this column, the largest elephant on every column, and then I take the smallest of all. The smallest of the largest elephant is still an elephant, and so it is larger than B star here, because even a small elephant is larger than a big mouse here. So we have in general, so that's not a proof, but that's an intuitive explanation and a way to remember. In general, we will always have that A star is larger than B star. It's called the max-mean inequality here. In general, there's not equality. There might be equality in some cases, but in general, we have strict inequality, except in some cases where we say we have a saddle point. We encountered this term already in theory of duality with Lagrange multiplier. It's related to that. If we use Boy and Vandenberg standard form, the optimal value of the dual is the max of the dual function, which was itself the result of the unconstrained optimization problem. So it was a max of a mean. That's the value of the dual here. Now, it can easily be seen, I don't do it, but that if you take the max of the Lagrangian here, it's very easy to compute. It's necessarily for a point that satisfies the constraint, and then the mean of it is the value of the primal problem. So one way to view the weak duality is the inequality we just saw before. In general, we know it doesn't work, except for when strong duality holds, which is true for convex problems of interest when constraint qualifications work, in particular for linear problems that are feasible. And then that's why we also say we have a saddle point of the Lagrangian, so that's related here. So small parenthesis, but we will need that more concretely for writing our optimization problems. Let's continue with, here is a variant, which is now not mixing mean and max, but is keeping mean and max together. I take the mean with respect to the y coordinate for every x, so that's a function of x, and then I take the mean. Or I change the order. What does it give? I close the poll in a second. Closing. The majority says B, which is correct here. It's also called associativity of a mean and max operations. Here you're taking you want to find what is the size of the smallest mouse or smallest animal. Then you can use divide and conquer. You can group the animals as you want. In every group, you find the smallest, and then you take all the smallest of every group, you compare all of them, and that will give you the overall smaller. In fact, that's one way of implementing a computation of a minimum in a logarithmic complexity. So that is true, and it's the same is true for max here. So take-home message, if there's only min or only max, you can be relaxed, you can do it in every order. It's like a summation. When you have a sigma sign, you have sum over index I and j, you can group them in whatever order. At the end, it works, at least as long as the summations are finite or absolutely converging. Here, the same happens with min or max. But remember, we can mix and match mins, we can mix and match maxes, but we be careful if we mix mins and maxes. If the mean of max and the max of mean, there should be a blinking red light somewhere saying, oh, be careful, that is dangerous. But only mins together or only max together, that's perfect. Okay, why do we do all this? Well, to solve our problem. Here is the problem we had before. If you put that into MATLAB or Python, you will not get anything useful. You will need to transform it into a standard form. Here I'm proposing two standard forms for this problem. Is any of those correct? Closing the poll. Closing. Majority says B, which is the correct answer. Of course, the only difficulty here is this phi function, which is nonlinear. So we need a closed form for this. And here it is. That's what we had seen. Phi is the max of three things, of three linear functions. So that should sound familiar. If we need to minimize something that has a max term, we have seen 2 weeks ago the max removal transformation. We can remove the max from the optimization objective by replacing this by another variable and imposing that the variable is larger than or equal to all of these terms here. That's exactly what we will do here. That's the optimization function. The optimization objective is the sum of objectives, and we've seen that from the max removal theorem that whenever we have to minimize something that is a sum of terms, if every term, some of the terms are maxes, then we can replace each of the terms by a variable and imposing that the variable is larger than or equal to each of the components of the max. So here there is one epsilon s. I introduce one variable, epsilon s, for each of those terms here, and I impose that epsilon s is larger than the three components of the max, which define the penalty, so which gives those constraints here. So we can transform the problem into a problem that's purely now linear, sum of over the control variables u over the entire horizon of the state, which are resulting from our actions, but are present in the optimization problem, and also the epsilon here. So we've added a number of variables here, and at the end, we have those constraints, which is the problem B. So that's first step. Now let's assume that for some reason, we want, the penalty that we had was the aggregates penalty. We said we care about paying a penalty for every time step. Let's assume for some reason that you prefer, for example, for simplicity or for whatever, to pay for the max penalty. You say, I pay the penalty once if I exceed the value. If I exceed it 10 times or 1 time, the penalty is the same. If I exceed it 0 times, there's no penalty. If I exceed, if I'm outside the band temperature. So we've seen that in robust problems, we often wanted to do this. That is, it simplifies the problem. So let's assume we do this here. It's a different objective function. Which would be the formulation that you give to MATLAB to solve this problem? If any of those two is a correct implementation. I close the poll in a few seconds. Closing. The majority says A, which is the correct answer. here is in full form a thing we have to maximize. The objective function is the max of the penalty, and the penalty themselves are max of certain terms here. Now we can use our knowledge now about, we know that max of max is a big max. So that's the max of all those things here. And we know it is simply the max of all, if we put all those terms in a big bag, so there are 3 terms multiplied by h steps, the values, all those values here, this is the overall max of everything here, associativity of max here. Now we can apply max removal, that is, we can apply one variable, call it epsilon, and then epsilon has the constraint that it must be larger than all of those terms here, which means epsilon has to be larger than this. There's a single epsilon, a single constraint for all the variables that link all of them together. Now it's interesting, it's fairly simple to do it in this direction. What is more difficult is to do it in the reverse direction. Very often we see that people do, because they do A or B, and they are unable to explain why they do A or why they do B, because the analysis is easy in one direction. So if I see this versus that, they both seem to make sense, right? If you put a penalty term and then you impose this soft constraint here. But now we understand what is the difference. In one case here, it corresponds to having here a penalty term, which is the max of all the penalty terms, whereas here it's having a penalty term, which is the sum of all the penalty terms. I'm sorry. Oops. So in conclusion, MPC is very simple, intellectually at least. Now it will lead to optimization problems that may be big, so that may require some tricks to make them work. In practice, we often try to make them linear. With an MPC, we obtain a nonlinear causal policies, and because it looks ahead, that's what makes it very successful. In particular, it's inherently robust because at every time step, it corrects all the inaccuracies in the forecast or in the model, because it starts from the measurement that is the last available one, as opposed to trying to predict an entire trajectory where errors would accumulate over the trajectory here. There are techniques to make it even more robust using robust MPC, very much in the way we used robust linear programs. We can add uncertainty about the forecast and make this robust. Or also scenario-based programming MPC, where instead of having one forecast, we have, for example, 3 forecasts, standard case with probability 90%, extreme low case with probability 5%, and extreme high case with probability 5% also. Then that can lead to still tractable, but more robust systems here. We will not see that, and in the lab you will have enough to do with the non-robust MPCs. Voila, that's all for this first part. We will do a break now and resume in 15 minutes, so at 10:30. We've seen a lot of control, and you're struggling with the lab to control a grid by controlling the generators. What we will discuss now is how to control the consumers, and that will also give us an opportunity to discuss of the generic system and market aspects of controlling a grid. So this is called demand response, and this will be much less technical than what we've seen before, but I hope nonetheless interesting. What is demand response? You probably met that term already. It has related concepts like demand side management. Some people make a subtle difference between the two, but not everyone. So in this course, I will not. It's the idea of manipulating the consumption to reach the control goal we want in an electrical grid. In all the labs we did, we control the generators, the battery, which is transparent to users. But we've seen a minute ago that we may also induce somehow the users to heat their house when prices of electricity are low, which is a form of manipulating the demands to operate at certain points in time. So that's the general concept here. It's very old, in fact. It's over a century old, and it has been implemented in practically all electrical grids already, but in very primitive forms. What was done in very old days is called ripple control, where you could have two different counters or two different circuit breakers at home, and you have to put your boiler, for example, on one of the two, and when the boiler could boil, was triggered by sending a signal through the electrical line, which is called a ripple. The electrical line, in principle, is not a communication line, but you can send some very, very low bitrate signal. For example, you can send a tone, a signal that has a frequency of several hundreds of hertz, in addition to with zero a tone of reactive power. If you want, zero energy is transferred through that, but it serves as a signal by a system that captures the signal and says, okay, this boiler can now be switched on or off. So that's a way that many grids had to control when the night shift would start, for example, to make it more or less variable. That's old systems. And essentially what we're trying to do is to make that more adaptive, that we have IT technology, and also renewables that cause more problems. But before, a level setting question, why do we think that people get so much interested on demand response today? I'm closing the poll in a few seconds. Closing. The majority says C. Well, there's no correct or incorrect answer to this because it's a matter of belief. C is certainly the obvious answer. The goal of this is to manage consumption to match production and is triggered by the fact that, unlike gas, there is no such thing in gas distribution networks. There is no demand response, right? Why is there none in gas distribution networks and there is one in electrical energy distribution network? Why is there such a difference? What's a fundamental difference between gas and electricity? Yes? Gas can be stored, exactly. There's no storage for electricity. There is, in cumbersome, complicated way, batteries. They're very expensive. In a battery, you can store the power generated by a grid for perhaps a day or fraction of a day. So you can store the power generated at lunchtime by the sun to use it at night, but you cannot store it over more than a few days, for example. You can store electrical energy by converting to mass into a pump hydro systems. You can pump into the mountain, into an upper lake when there is too much, and then turbine it back into electricity. But that involves a conversion. That involves two lakes and a mountain, so it's a complicated process. Whereas gas is naturally stored in tanks, it's stored also in the pipes. So that's the major difference. Electricity cannot be stored. That's a major problem of renewable energy and of electrification in general. Demand response is one way to mitigate the effect of that. It's a form of replacing storage by manipulation of users. In fact, if you think about it, what David McKay's house was doing, at 6 o'clock in the morning, electricity became very expensive. So what it did is, at 5 o'clock, it started raising the temperature of the house to 2 degrees more, and then it stopped heating at 6 o'clock. and then the temperature dropped, but since it was a bit higher, it was still comfortable. In fact, what this has done was to store electrical energy in the form of heat into the house at 5 o'clock in the morning. That heat will, of course, be lost and dissipate, but would be used to heat the house and keep the house warm at the time when electricity is large. So we can view demand response as a way of manipulating, in particular, thermal loads to store energy in their inertia, hoping there's not too much leakiness, and convert, in some sense, the problem of electricity storage into one that's for users. Why did I put dotted line on save energy? Well, because, in fact, we will see it can also be used for this, or the desire would be to use for this. If I instruct everybody to stop using energy, I hope to save, because if I say, now don't do this, then you don't do it, so you don't burn energy. But it's a hope that may be correct or not correct, because, of course, if I don't heat now, like we've seen in David Mackey's house, we heat before or after. So is it really saving? That is one of the questions we will discuss. The primary use of demand response today is for doing what is called peak shaving. Peak shaving means cutting the peak. Here is an example of the France consumption in November on different years, on an average year and on a cold year. And we see that the demand peaks, but the duration of the peak is very small. Now you could say for a system that's a bit flexible, that's no big deal, but electricity systems are not very flexible, in particular the generation side. And we've seen that with the recent events last year, there will be a shortage of production because all of a sudden, all Western European or European countries refuse to import gas from Russia because of the aggression war of Russia against Ukraine. So all of a sudden, the generation capacity has been reduced. And in fact, that's one of the problems in all countries in the world. The only way we know how to generate electricity without any problem is by using coal. That's the number one availability in terms and cheapest way in terms of worldwide. And second, petrol, and third, gas. All of those, of course, we would like to avoid because of the climate change problem. So we want to not burn coal as much as possible and reduce petrol, and if possible, reduce also entirely gas. And if we do this, then we have a problem. We have a problem of consumption. We can replace it by a problem by other techniques, but that's very expensive things. So if I have a peak consumption here and I want to provide this peak, I need to put in place the capacity that will be used for example, if I want to be above this bar, this will be used only on a very cold year. So there will be some years where I never use it. And even if I use it, I will use it a few hours for a few days in the year, so I'm doing an investment that will not be very easy to amortize. So that's one of the motivations. If we could find a way to avoid this peak, we could dramatically reduce the cost of the grid here. There is another, so that's, I would say, peak shaving. And if we don't do peak shaving, if there is a problem here, what will be the result? If we don't have enough capacity, that would be load shedding. If the operator of the network, of the grid, the transport network, Swiss Grid, for example, sees that there will be a shortage, then they will declare that we cut power availability, but that will be planned and managed. So we say, for example, to EPFL, next week, that won't happen now because the winter is behind us, but there is such a plan, a contingency plan in Switzerland and in every country that says, well, tomorrow you need to not give class at EPFL because we want to reduce, or there will be only 20% of the power that you're supposed to have at EPFL campus. It's called load shedding, and it is planned, but it's unpleasant, but it's manageable. There is worse than load shedding, which is called blackout. Blackout is when there is no power and it comes as an accident. It can come due to a failure in the control of the grid. As we have seen, the grid is controlling everything doing OPF. We've seen that OPF is a hard problem to solve. If you do a mistake in your OPF and whatever, your software has a bug or the nonlinear solver doesn't converge or whatever, there might be problems that cause one problem that is similar to a hardware failure. Most problems are in fact hardware failure. For example, a nuclear plant, we detect a leak in the cooling system, then we need to stop it. Or in a gas generator, we detect there is some crack in the turbine, or some other system has quagga muscles that are obstructing a tube, or whatever system. I mean, any physical system may have failures. We try to avoid them by having preventive maintenance, but they can happen. If they happen, then the grid operators will use a number of reserves to mitigate the problem. And one of the reserves might be to do demand response, or if this fails, then there will be a blackout. And the blackout is much more severe than the load shedding, because the load shedding is planned. A blackout means we interrupt the supply. What happens when we interrupt the supply is called a cascading effect. If I interrupt the supply, for example, we break a line between France and Switzerland, and we're at a point of time where there were a power transfer from France through Switzerland to Italy. Then Italy does not receive all the power it was supposed to receive. Then what will happen is that, because we've seen that the flows of power are dictated by the complex voltages and not by routing tables, so there will be the flows will change everywhere on the grid. That might cause ampacity limits to be violated on some lines. That might cause those lines to automatically trip. So there is circuit breakers that may come into action that could cause another line to break, which might make the problem worse. If a line breaks somewhere, perhaps there's less power coming somewhere, which causes another line to carry more power, etc. It's called a cascading failure. When that happens, an entire grid may be disconnected. That happened in 2003 in Italy, where all of Italy had no power for an entire day. I was in Italy at that time. It was not me who caused the problem, but it was funny to see what happens in a country when there's really no power during an entire day. It's complete chaos. Nothing works. The gas stations don't work. The harbor control system doesn't work. And nothing works. So that's very bad. A blackout is very bad. People can die from a blackout, right? People who had a medical condition that necessitates some help and the hospital doesn't work, the emergency system works partly but not fully on diesel generators. That's very bad. So we want to avoid this. How do we avoid this? Of course, we plan in the grid for reserve. We will talk about reserves in a second. And those reserves, so we put a safety margin, but part of the safety margin can involve reducing consumer load here. And of course, all of this is exacerbated with wind and solar energy. All energies that are stochastic make things worse because the disturbance is failures in the case I mentioned. The disturbance in the case of wind and solar energy is the forecast error. For solar energy, it can be kept small. For wind, it's much harder to keep it small. The wind is much harder to predict for probably a physical reason. So we have forecast errors on a day-to-day basis for wind, which is order of 10–20% here. So there is a disturbance here that comes to play. This disturbance calls for more reserves. More reserves, more means more costs for operating the system. But the good news is that what can be the subject of demand response? Of course, it's things that are easy to shift in time. Those are so-called elastic loads. Non-elastic loads are what we're doing now. There's this beamer. The light in this class is not very elastic. I mean, we meet at 9 to give class. There's not much we can do to save the power that we're using for this class to happen. If I could draw on the board and use a candle to light, but that would probably not be very efficient. So there is a lot of non-elastic loads, but there are some elastic loads, and the mass of those is increasing as we see an electrification of energy systems. Electrification of heating systems. We replace oil and gas heating systems and coal heating systems by heat pumps that consume electricity. And we replace also cars in the future. We started replacing cars that burn gasoline or diesel by electric cars. So, and those are huge masses of electricity consumption. And they are flexible in the sense that a car has a battery. So, except if you're going on a specific trip, but a large fraction of the cars will have some flexibility on when they can charge and how much they charge. And the same is for the heating system. We've seen that the heat pump of David McKay could be used to have some flexibility, at least over some limited time scale. Fridges and freezers, thermal centers, data centers have even more flexibilities. Data centers, apart from the time where they're doing really mission critical jobs, most of the time they are doing things that have practically zero societal value, like training ChatGPT or things like this. So you could adapt the power that they use for this to the availability of power on the grid. So this is, some companies are working on that, but that's not very widespread. So there has been a number of deployments of demand response with modern information technology systems that I will describe, that will discuss some of them. Here's one that received a lot of attention. We've discussed the David's house. That's one example here. So using an MPC with a controller that controls the heating system. Admittedly, it's not really done for individual houses. Not many people do that for their own houses, although David McKay did it for his house, but you typically do it for bigger building, like the EPFL or campus heating systems or bigger systems, where the cost of having a computer that does the MPC is amortized easily over the entire, and you have a computer, you have a SCADA to monitor your heating system anyhow. Here's another example that was conducted in Norway. Norway is a country, you could say, that has a lot of energy, so they don't care. Why should they care about all the problems we're discussing here? They're an oil producer, but they want to be green, so they don't use oil to generate energy, but they have lots of mountains, so they have a lot of hydro. But they have another problem. They are a 1D country, one-dimensional. It's a line from south to north, and that means the grid is very, very long. And the problem is the grid, in fact. And the grid is fragile and very expensive because the country is not very dense and is one-dimensional. In a two-dimensional countries, I mean, the surface of the grid with respect to the total length of the grid with respect to the population is smaller than if it's one-dimensional. So one-dimensional countries like Norway have grid problems. The grid is very expensive. Therefore, the quality of the service of the grid might be an issue. And it might be an issue that leads to what is called large locational prices in some parts of the country. We have seen when we did the OPF, when a small grid with 3 examples, that the prices of electricity could be very different, or the marginal price could be very different on one bus than at the other. This is exactly what is happening in countries like Norway, where, because the grid is limiting, at some point in time there is a lot of power, but it's far away from the place where you are. Then at this place where you are, the grid is limiting and you need to use another form of electricity, another generator, which is more expensive. So that has happened exactly in Norway. And this is prices in some, no, sorry, I'll show that later. So very high prices have resulted, or larger prices have resulted in some parts of the country. To mitigate this, they introduced a demand response program where they advertise hours ahead of time. They advertise hours during which, hours of the day, which here are the morning peak and the evening peak, so the Norwegian morning and the Norwegian evening. I guess it's not the same all year long, where during some periods of time, prices might be higher. And then the prices, which are given here, you see, they can become significantly higher. And then users are made aware of this, and you rely on users so they distribute it to users stickers that they put on their washing machines, for example, and then you are reminded that if you start your washing machine now, there is a risk that the price is very high. So perhaps if your washing machine has a timer, you let the timer start it a bit later. That's an example. And I give a reference here that concluded that it did have a visible effect on reducing the load at the peak times, that had an effect that reduced, if you remember our problem with the 3 nodes, the cost, the marginal cost depended, of course, on the load here. If you reduce the load at some point, you might reduce the marginal cost, and that worked. So that's an example of demand response deployed in a country with an effect on the locational marginal prices here. This is exactly the point that was made. So here we have 2 nodes in the network, and one of the nodes, which is probably, I'm not sure where in the country, probably further north, and where the price becomes much more expensive than the typical value here by a factor of 6. And that happens because before they implemented this demand response program. To understand what is the effect of reduction of load on prices, we look at what are called price and demand curves that we will discuss in a second here. Sorry, not price, supply and demand curves that we will discuss in a few more minutes here. Closer to us in Switzerland, there are, yes, question?
If you do this, don't you just shift the peak demand by 2 hours? And if anything, like increase it, if everyone sets their machine to start at 8 p.m., then the peak would be even higher.
That's a very good point. It's called the rebound effect. Well, if everybody shifts it, then you just postpone the problem, and we will discuss that again. Yes, that's one thing to take care of. If you simply shift a big demand, you have a rebound that may make things worse. But if that happens at a time where, for other reasons, the load was lower, that might be better. You have this peak, but if it comes where another load has been reduced, typically office buildings, for example, that are closed, they're not heating, they're not lighting, and the computers are not working, then you prefer to have that peak at that period than now. But that's a very, very good point that we will rediscuss. Closer to us, you can find services of this type in Switzerland, where you have, for example, an interruptible supply or a time of use tariff. An interruptible supply is something where, for example, the service is available 20 hours per day, but not more. So if you connect, that's typically for boilers, you connect your boiler or your heating system to a given socket on the wall that's fed by Romande Energie. And Romande Energie will decide when they allow it to work or not, but they guarantee that every 24-hour period, it will work for at least 20 hours. But they have the freedom of cutting you off for 4 hours every day. If you know in advance, you can do an MPC to do that. If you don't know in advance, then you use a boiler or a big thermal mass to store heat into something such that is large enough such that you can live for 4 hours without the service. So it's typically used for boilers. In France, very recently has been introduced this year something also very similar, where the motivation was to reduce the peak because of the difficulty of the grid to generate all the peak power that would be otherwise required. So they offer you a service where the prices are like this here. You see that it's the French way, so the days are colored with the colors of the French flag. And when a day is red, it is there are still 2 peak and off-peak hour prices. When you are at the peak hour prices on a red day, you see that the price of electricity is a factor 6 of what it is otherwise here, 4 to 6 otherwise. So very expensive. So if you heat your house with resistive heating at this time of the day, you will quickly have problems with your bank account or with your banker. It will cost you a huge amount of money. And they advertise this more than a day ahead. So at 11 o'clock before noon, the day before, you know the color of the following day. And therefore, you better stop heating entirely during that day, or you go to a neighbor or something, you stay in the office, you don't work from home on that day, whatever freedom of action you have, or you heat your house and you close all windows and everything the night before, so that you know you will have no heating on that day. And this is possible because we have smart meters. It's possible because now we can control the price and change the price with some flexibility. Here, the flexibility is in the on the energy provider side, and here too you have some limits on how many days it can happen in a year, and that's one way. And we were told that it was effective in reducing the peak. This winter, which is the first winter when it hasn't been introduced. That's a fairly coarse implementation of demand response. We will see more subtle ones, but before getting to those more subtle ones, we need to discuss the problem of balancing the grid. So a grid like the ones we do in the lab, or the continental grid of Europe, for example, must maintain power balance at all time scales, in particular instantly. Whatever is produced in the grid must be consumed somewhere. Otherwise, if it would not be consumed somewhere, it must be consumed officially or not. If it's not consumed officially, that means some heat will dissipate somewhere. So something will burn or explode if you have overproduction. And if you have underproduction, you will have voltage drops, and some generators might stop working because you're pulling too hard on them. Now, the thing of interest is that in an alternative current grid, in an AC grid, like we're using practically always, the power imbalance alters the speed of rotating masses. So traditional grids are made of big generators, which are rotating masses that are fed by some energy source. For example, a diesel generator. You burn diesel into an engine, and then that makes a dynamo rotate. A nuclear plant is the same. A nuclear plant just produces vapor, heat. You heat water, you got vapor, and this vapor is like a locomotive of the last century, is used to rotate a turbine that produces electricity. And the same for coal-based generators or gas turbines. You have rotating masses, and at the industrial scale of a country, those are big rotating masses. What happens when there's an imbalance? For example, when I start a kettle, I consume more than a second ago. So the grid will need to produce more. What happens is that you pull more, and those generators, they feel that you're pulling more, and they slow down. It's like you and me on your bicycle. You're a flat terrain. All of a sudden, it becomes steep, then you slow down, unless you change gear. But if you don't change gear, you will simply slow down. So the rotating speed reduces. The rotating speed in synchronous AC systems is directly dictating the frequency of the electrical currents. The frequency, which is 50 hertz nominally in Europe, 60 hertz in some other countries. But it's only the nominal value. That value decreases a bit when there is an imbalance, or increases a bit if all of a sudden there is more power being generated, because it's like you on the bicycle. When it goes down, then all of a sudden you go faster. That's what happens in a grid with big rotating masses. So there are small imbalances that translate into small frequency differences. You've seen in the previous modules how to estimate the frequency with PMU. You see that it varies all the time. But there is a balancing system, which is the mechanical inertia. If you pull more on a big rotating mass, then it slows down, but by slowing down, it returns some of the mechanical inertia that was when it was turning. It had a mechanical energy that is delivered when you slow it down, which balances in the short term. There is a balancing effect of these big rotating masses, which stabilizes the grid. But of course, it stabilizes it for a fraction of a millisecond. If really there is more power being demanded than what is produced, this will smooth the imbalance, but the imbalance will exist, and then something bad will happen sooner or later. So the first level of reaction is called droop control or primary frequency control, where all generators of those big rotating masses have what is called a governor. Think of it as the gas pedal of a diesel generator. Your diesel generator, when you pull more on it, then its speed reduces. You can hear it if you are in the noise, or the sound, some people call it a sound. The noise of the generator changes. It becomes more or less, the pitch raises or goes down, depending on the speed at which it turns. And if it's a generator that's connected, so the frequency of if you have your own diesel generator at home, the frequency will be very bad. It will not be 50 hertz. It will dramatically fluctuate. But in an interconnected system like continental Europe, the frequency varies much less. So those big generators, what they do, when they feel that it's getting tougher, they put more gas. It's like if you're not on a bicycle but on a scooter, when it's going up, then you put more gas to compensate and keep your speed constant, or you brake to reduce the speed when it's going down. That's exactly the droop control. That's the governor of generators. So all generators that are connected to the public grid must, by grid code, implement this, which provides a stabilizing feature, which also means that those generators must keep some flexibility margin for the control of the grid. For a nuclear power, for a nuclear plant, for example, it means that we release some vapor into the air to reduce the power a bit. So we never use 100% of the mechanical power of the nuclear plant. We use perhaps 95% of it, and we use a few percent of it as a flexible energy that we can throw out in the air or use in order to provide this balancing effect. I said all generators do this, but it's not true. Your PV panel on the roof doesn't do this. So many renewable energies don't do this, and that's one of the problems, is that the amount of stabilization provided by the traditional generators is going away. So it will have to come back from somewhere else. That's called primary frequency support, and it is triggered by frequency. Those generators, they just observe the frequency of the power using PMUs or even more primitive systems. And as soon as the frequency varies by minuscule amount, we're speaking of fraction of millihertz or several millihertz. When it varies by a few millihertz, then they will give more or less gas using a simple linear control law based on a fine feedback control. That's the first, that's how things work, at least at the primary frequency level in an AC grid. And the first thing also to remember is that the deviation of frequency from its nominal value is an implicit signal of power imbalance. This is why, in fact, this is often called in technical papers or technical user guides, frequency support. We're supporting the frequency. We're making the frequency, we're helping the frequency get to its nominal value. But in microgrid, assume you have a microgrid on an island or a boat or something that's not generated to the main grid, that is fed only by power electronic. For example, your slack bus is a battery. That is very often. The slack bus today is a diesel generator if you're islanded, but in the future, hopefully, will become in more and more grid a battery. If you have a battery, you don't have a big rotating mass, right? The battery doesn't feel that things are getting harder or whatever. It will just feel in some other form, perhaps by voltage drop or some other mechanism, it will see that there is power imbalance. In contrast, if you, in such a grid, the frequency is done by the converter electronics. It's 50 hertz. The only difference that you see are due to the instability of the oscillator that computes the frequency, which is minuscule. We're talking of thousands of millihertz. So there is, we've seen when we talked of, at least those of you who took the advanced course and talk of power of the time synchronization system, we see that an oscillator is never perfect, but the variation is minuscule. So for all practical purposes, the frequency is synthetic. and does not fluctuate significantly. And worse, the fluctuation is not due to power imbalance. So there is no frequency support in such a grid here. So frequency, but what you need to do is to do other mechanisms, and we will discuss some of them. In the lab, you do some of them. You might measure the power and then automatically decide to start more or less the battery, for example. A battery will have another mechanisms also, which is to be like a voltage source by forcing the voltage to be at a nominal value. And by forcing this, the first symptom of imbalance will be a drop in voltage. And by re-establishing voltage to a higher value, this is how it will do its slack bus job of providing the balance here. In a larger grid, like interconnected grid of a country, or in a country like Switzerland, we are part of what is called the Continental Europe interconnection, which contains today also Ukraine. And then when this drawing was done, Ukraine was not yet part of it. In such a big interconnection, which contains all of continental Europe and the continental part of Denmark, there's another interconnection system, which is the northern part of Denmark, the island part of Denmark, and the Scandinavia. There's another system, which is the Great Britain, and yet another system, which is Ireland. Northern Ireland and the Republic of Ireland are another system. So each of those are interconnected systems on which the frequency is, practically speaking, a global quantity. So power balance is maintained globally in each of those systems. Such systems are interconnected, but they don't share frequency. For example, there are interconnection links between continental Europe and Great Britain, but the frequency is not the same at two ends of the link. Those are DC links. How does it work? So in such a system here, all systems do what I just mentioned before, droop control, which is called a primary reserve here. So if there is a small problem, for example, this is an example of a nuclear plant that had to be disconnected because of an alarm. There was a non-planned incident that was detected, hopefully just a preventive incident. We detected that there's something to check. We need to disconnect it from the grid. So it disconnected from production. Nuclear plant is probably still connected to the grid, hopefully, but is not producing. So we lose a lot of production, but because a nuclear plant, perhaps here it was half a gigawatt, 500 megawatt, which is large for a country like Switzerland, but it's small at the scale of Europe. So it has an effect. We see it that all of a sudden the frequency drops. It doesn't drop dramatically. It drops by perhaps 60, 70 millihertz. So all systems in Europe see this quasi instantly. So all generators in Europe, including in Poland, in Switzerland, in Spain, in Portugal, in Greece, they all produce more using droop control. And we see that they're trying to ramp up here. The production is increasing here. And also that prevents that from being a more catastrophic drop that could lead into a blackout. That's the first thing that happens. Now, this is still a big loss, so this is not sufficient. So the primary frequency control, all countries being in pink here, means all countries here are helping the grid to recover from this loss here. And then the grid code says that that's okay just for the very short term to prevent cascading failures, but it's the responsibility of the area where the failure occurred to solve the problem. So RTE, in this case in France, uses a second scale of reserve, which is called the secondary frequency control, or the secondary reserve. Secondary reserve is not based on frequency, it's based on explicit signal. It's also called load frequencies control. In the US, it's called automatic gain control. And this is an explicit signal that is sent to some dedicated generators that participate as a service into this system. For example, if you have a generator, let's say you inherited from a grandfather gas turbine somewhere of 300 megawatt, then you can sell to Swissgrid a secondary regulation service, where SwissGrid will come and verify whether your installation is able to react to their signal. And you will be paid for being in standby. And you will also be paid for whenever you burn gas for providing the service. So this is what will happen. All secondary reserves will be activated inside France and will generate it, will increase their power. And after a few minutes, then this will bring the system back to normal. At least the rest of the grid, the frequency is back to 50 hertz, and the rest of the grid doesn't use their primary reserve to stabilize the grid. So the problem has been compensated in the short term, but now you still have a longer term problem. You have a nuclear plant that is not working. So the secondary reserve will work for some time. The secondary reserve by grid code should be activable within minutes and should last for 1 to a few hours, but not more. So there must be a replacement for this power plant that is no longer working. This is called a tertiary reserve. So those are called standby devices that can be activated when they are needed, but that may require some time. Here, 15 minutes here. So those are reserves that receive money just to be in reserve. Those are typically gas turbines that are not working or that working at very slow speed to burn a minimal amount of gas. And when you call them, then you start them at a higher, you put them at full speed, which may take several minutes to work, and they should be able to work for long periods of time. So that's how the grid works today. And because now we have more and more stochasticity of the generation and less primary reserve, those secondary and tertiary reserves are increasing. So there is a market for those. If you have your gas turbine inherited from your grandfather, you can go to SwissGrid and offer it as a service, secondary or tertiary reserve, and you will see that the money you receive for that increases now. It has more value now than last year, for example, and will have more value in the coming years because the uncertainty, the disturbances that will be on the grid will be larger. Here it's a disturbance due to failure, but this lives in a constant disturbance due to randomness of renewables. So these three types of reserves are called frequency control because the frequency is the symptom of power imbalance, but in reality they should be called power balance reserves. Now, people have anticipated that the grid of the future, the one that we start to see now and that you will work with, will have more and more reserves, needs for reserves. So people have started to try to activate demand response for providing a reserve, and we'll see a few examples of that. Question?
Before you talked about countries like in Europe connecting their grids together for more stability, what happens in, for example, like in Asia, if you have like the Mekong Basin where you have countries that are less organized, less wealth, do they also connect the grid? Is it worth it for them? Or in Singapore, for example, you have a very developed, rich country surrounded by Malaysia, Indonesia, which would have like a much less stable grid. Would they still connect everything? Is it worth it or not so much?
It depends. It's very variable. I don't know all cases in Asia. Singapore, I know, is an island. It's not connected. It's connected, but it's not connected in the sense of sharing frequency with Malaysia, for example. So Singapore is an island, and of course, it's a small system. So the cost of reserve for Singapore is much larger. So Singapore has a huge reserve compared to Switzerland, for example. Switzerland, for many things, benefits for its position. In Switzerland, we think we're better than many others, but we're also better located. We're located in the Alps at the intersection of traffic north, south, east, west. And that happens for electricity also. So the Swiss grid is in fact carrying 50% of the energy that transits in the Swiss grid is going from outside Switzerland to outside Switzerland. So it's transit energy. So we're at the center of a big interconnected system. So even if there's a big failure in Switzerland, it's a small failure at the scale of Europe. But Singapore is different. Singapore has a need for a big reserve. And here's another example, which is not as bad as Singapore. but is Great Britain. Great Britain is much larger than Singapore, but much smaller than continental Europe, and is an island, electrically speaking. So they must balance their power at the scale of Great Britain. Even worse is for Ireland. I don't have figures for Ireland, but this is a project that was also adopted by Ireland. So one of the ideas that went a long way was eventually not developed, but who knows, it might come back. This idea was to use the fridges for providing primary frequency support. Why the fridges? Well, because fridges, believe it or not, are a large fraction of the use of electricity, and they're working constantly. Not literally constantly. A fridge compressor is typically on and off. It goes on to reduce the temperature. It's a thermostat-driven system. It reduces the temperature. When the temperature is low enough, it stops working, and it has a dead band, like we've seen in the thermal system of David McKay's house, except now we want to cool down instead of heating. This is how a fridge works. But if you take a country, at the scale of a country, you have millions of fridges, and all together they form something very uniform, and that's working all the time. And the idea was, at the time scale of primary frequency support, then you could play with that. For example, you could say that if there is all of a sudden a power imbalance due to loss of a generator, you could instruct all fridges to not do what they were planning to do now, but postpone it by 1 or 2 minutes. For most fridges, it will be good enough. Most fridges are closed. Of course, sometimes you open them, but most of the time they are closed. So when they are closed and nothing is happening, the temperature decays or increases very, very slowly. If you put a small safety margin in the dead band, the temperature should be, for example, between 3 and 5. Instead, you want to never exceed 6. Then if you have a secondary margin that says the normal operating range is between 3 and 5, and now if I have a signal that says, well, perhaps you want to delay a bit, then perhaps I can go up to 6 here. So that's exactly what has been proposed. So people have developed chips that you can put on the electronic of a fridge that sense the frequency of the AC current. They sense the frequency, and they instruct the fridge. They put the fridge in a mode where, depending on the inside temperature, it will go off or on by. So if it's in a period where the frequency has dropped, for example, then we might extend the off period. So the fridge is on/off. We might delay a bit the time at which the compressor will start again, or vice versa, if we're in a period where the frequency is larger than the nominal value here. So this went a very long way. People have developed chips, and it did not get approved eventually for reasons I'm not sure. But the latest computation was that 1 gigawatt of reserve could be offered to UK grid with this system here. 1 gigawatt of reserve, that is, if you deploy this, if you make it mandatory in all new fridges, then you save 1 gigawatt gas turbine, or 2 500 megawatt gas turbines, and you will not burn any gas for that. So that's an example of demand response at high frequency that could be provided. As I said, it was not deployed, but who knows what happens in the more and more tension on the electricity grid that might come back. There were similar studies that were done in the US, now not with the fridges, but the heating fans. The heating fans are, so in the US, most heating is air-based, not like here where it's water-based. We heat water that will circulate in pipes to heat the room. In the US and in Canada, it's essentially you blow hot air into the room, which is much less nice. The air gets dry and so on, and it's noisy, but that's the US. And the idea that was here, if you control the heat of the fans that circulate the air, because if they blow a bit less, then the power is less, so they will heat less. They provide less power, which eventually would not be good enough. But if you do it over a short time scale, it's very similar to controlling the heat pump that we discussed of David McKay. It's it will induce temperature fluctuations, but it will also affect a lot the power consumption. So one study was done that concluded to the fact that 70% of the secondary reserve in the US, that's the reserve in the US at that time, which was 10 years ago. Now the reserve in the US increases, so this percentage drops a bit, but could be provided by heating fans alone. There has been other studies about the pumps and the swimming pools in the southern part of the US, where they came also to large numbers. So a large fraction of the reserves that we need in the grid could be provided by automatic control of adjusting what we're doing with houses, heating, cooling, and cleaning the swimming pool. Here is another more high-tech example that was developed in the smart grid project at EPFL and by the company called GridSteer, where using on a microgrid that has a battery, you can provide primary frequency support by adjusting the power that the grid is consuming. You can adjust, like we have seen, by playing with the fridge or the fan, of the speed of the fan or the heat pump. But when all of this is exhausted, you can also adjust if you have some battery. Many systems have batteries. For example, if you have solar panels, the solar panels typically produce in the day, in the middle of the day, and you want to use the electricity in the evening or in the night. So many solar installations have a battery. So you can use a small fraction of the battery to provide primary frequency response. Here you see, for example, the frequency of the grid. It was measured here at EPFL. And here you see what is called a dispatch plan. The dispatch plan is how much this grid has committed to the market in terms of consumption. If you go directly to the market to buy or sell energy, you need to produce a plan. If you don't go to the market, if you go to a provider like Roland d'Énergie, Service Industriel de Lausanne, they do it for you. They do the dispatch plan for you. You don't need to say to your operator when you would what is your production tomorrow and the day after, etc. You just pay for whatever you use. But they have to do that for you, because when you buy, at the end of the day, those system operators like Swissgrid, they arbitrate the market, and they have to make sure that everything that is consumed is produced and everything that is produced is consumed. So every operators have to say ahead of time how much they will use, they will consume, and they bid and try to find somebody who matches their consumption. In this grid, assuming we do this, here's a dispatch plan. So the dispatch plan is in green. Let's say, for example, 0 here means we are neutral, we are autonomous during this period of the time. Here negative means we produce, that's the middle of the day, and in the night we consume. That's a dispatch plan. Now, the idea that many are pushing to solve the problem of more renewables and fewer rotating masses is to say, well, some of the systems should provide primary frequency support, and this can easily be done if you have a fast real-time control of your battery. So essentially what we're doing in the lab, but imagine you do it every 100 milliseconds instead of every 15 minutes. Then you can adjust the power that is generated by this grid. So what happens is that we measure the power consumption of the grid with PMUs, and then the battery takes a decision to consume a bit more or a bit less. So we see that in blue is the true production. Sometimes it's less, sometimes it's more. And we see that it is less here, for example, at a period of time when the frequency of the grid is higher than the nominal value. So when that happens, primary frequency control, the droop control says we should slow down the generator, we should produce less. So here we do it synthetically, and the converse happens here when the frequency is lower, we produce a bit more. So that's music of the future. Here it's more or less experimental things, but we think that in the future there will be markets and opportunities for using power electronics to provide also some frequency support by adjusting. Of course, you need an adjustable source, which in this case is a battery. More concrete systems that are deployed today. Here is one which is in France, Voltalis. In France, we mentioned these variable prices where EDF, a major and state-owned energy producer, says to you, on a red day, you will pay 60 cents instead of 12. That's one crude form. Another more subtle form is done by a company called Voltalis, where they introduce what is called blue pods that they connect to your electric panel. They come to your house, they install a panel and a device on your panel that will control, disconnect, it's an on-off system, your boiler and your electric heating system. In France, there's a lot of electric resistive heating systems, much more than in most parts of Switzerland. This is because France has a long tradition of being a nuclear country. So when nuclear energy was developed in the 70s, there was the myth that it would be like the internet. The internet did not exist at this time, but in the internet, information is abundant and it costs nothing. You can have more than you need, in fact. There was the same myth about electricity. Nuclear would solve the energy problem once for all. So energy is not a problem. And truly, electricity cost at that time 5 to 6 cents in France. So people did very cheap heating systems, which are energy inefficient. But since if energy is cheap, you don't care about being efficient. And boilers are also, cheap boilers are also easy to do. The advantage of a boiler is that it is a form of storage. So boilers are very much liked by electricity operators because they give them some storage, which is much cheaper than batteries. In fact, you heat the boiler. Well, a boiler is easy to insulate. It's a closed thing, a closed system. You can heat your boiler at 2 in the middle of the night and use it to take a bath the following day at 5 p.m. Right? There will be very little loss of power in the boiler. The only drawback, if you have a colloq and 5 people, the 5th one might have no hot water if the boiler is empty and if the boiler is not large enough. But that's a very standard use in many countries, including Switzerland. The idea of Voltalis is to send a signal to these blue pods that will disconnect, that will switch off your resistive heating system and your boiler whenever it receives this signal. They guarantee that it would happen at most 60 minutes a day. Now imagine you're the company Voltalis. They've deployed millions of those devices. Now they can go to RTE. RTE is the French equivalent of Swiss Grid. When RTE is saying, for example, oh, I need 1 gigawatt of power in 2 hours from now, then Voltalis raises their hand and say, we can do it. In 2 hours, we will send a signal to 10 million devices that will switch off, that will reduce the consumption by 1 gigawatt, according to our estimations. And for RTE, is the same as having 1 gigawatt of extra power being generated. This is the business model of Voltalis, so they work on that. And you could say the user should be paid a bit, but the users don't get paid. Voltalis comes to your house, installs it for free, but you don't receive any money for it. But they claim that by doing that, you're being green and good citizen, and since it costs nothing to you, so millions of people accepted to do this. In other countries, which are more picky about their money, like the Anglo-Saxon countries, users receive a small payment for accepting to be part of this. So there is PeakSaver in Canada, in the USA, a number of, and other countries, a number of similar systems have been deployed. Switzerland also has deployed a similar system. The company that I know that does this is called TICO. It does the same, but not with a resistive system, but with heat pumps. So TICO installs a device that will connect to your heat pump, and will send this is the map of all the heat pumps 1 year ago that were controlled by TICO. And but the idea is the same. Now TICO is at the head of not millions like in Switzerland, but tens of thousands of heat pumps. And if it decides synchronously to send a signal that will do like David Mackay's house, except now it's TICO that decides don't heat now. And if you do it hundreds of thousands of times, this will have a visible effect on the grid. It has the same effect as additional generation. What is the business model of TICO and Voltalis? Well, in the case of TICO, they buy what is called a secondary reserve service. So they have a contract with Swissgrid. What they say, we provide you a secondary reserve. Remember what secondary reserve is. Whenever there is imbalance somewhere in the grid, in excess or in default, Swissgrid sends a signal, an explicit signal, which every few seconds, and then you should adapt the power consumption or generation to that signal. Yes?
These like tens of thousands of installed patients, do you have any like results that show us the benefits?
Yes, I will speak about that. No, not of TICO, but for Voltalis, so we have a report that. Of course, there's a small catch, but we'll discuss about that. The business model of Voltalis is similar. It also goes into secondary reserve, but it also goes directly into the market. There is an intraday market. In addition to the reserve is continuous. You get paid for capacity. If you sell a secondary reserve service, you say, my capacity is available, so I get paid for making it available. In addition, there is called an intraday market where during the day, for example, now, there might be, Swissgrid might say, we have a problem at 5 o'clock tonight. We want more generation at 5 o'clock tonight. Who is willing to sell 500 megawatts of power to the grid tonight? And then Voltalis raises their hand and say, we can do it. We can, they don't generate anything. They just reduce the power. Lots of problems, economical and law problem around this. It's not clear that by doing that, you should be paid 100% of what you're paid, because at the end of the day, those systems have subscribed, for example, to EDF to receive energy. And if Voltalis cuts them, then EDF doesn't receive the payment, but it is Voltalis that receives it. So it's very complicated to settle, but this system are deployed and they work. There has been even a proposal by some research groups at IBM to deploy, as far as I know, it was not deployed, but who knows, it might get deployed again, to go even to the tertiary reserve using, for example, boilers, because boilers have more inertia. The idea is the following. Here is, as a fraction of time, the integral of the energy deployed to all the boilers in Switzerland, typically overnight. And this is, so it varies every day. Not everyone uses showers in the same amount every day. It depends on the water. If it's on a cold day and the water coming from the pipe is colder, you need more energy to bring it to the adequate temperature, etc. So there are seasonal and daily variations, but you can have an envelope on the worst and the best case. You can have a lower and an upper bound on those curves here based on statistics. And then the idea is the following. This is my predicted envelope for tomorrow. Then I will, if I control the boilers, if I can send with Voltalis type of schemes, I can send signal to boilers. I could prepare a trajectory, which is the green one, the dotted line here. That's the trajectory that I plan for tomorrow. So this trajectory depends on when I start every boiler. Of course, it's not as smooth as this. There are small fluctuations. But if you integrate hundreds of thousands of boilers, you will have something like this. And then the idea is if I take a trajectory that is far enough for the bounds, I can deviate from this trajectory when I receive signal from Swissgrid. For example, the grid is saying there's a power outage somewhere, a big power outage in Switzerland. We need a bit of a large recovery power. Then I can modify the trajectory of my boilers like this here. I will need to come back here. But during this period here, you see that I reduce, this is the slope of this curve is the power consumed by all the boilers of Switzerland. Now it gets to zero for example, 4 hours. So during 4 hours, I have stopped hundreds of thousands of boilers. And this is the same as adding several hundreds of megawatts into the grid here. In contrast to the previous things that can be done a bit longer because boilers have more inertia, more reserve. So that's another example where you could provide tertiary reserve services with demand response. That kind of things has been tried and deployed on an island, on the island of Bornholm, which belongs to Denmark, but is located off the coast of Sweden. Like every island, things are always complicated in the islands. Even if they are connected to the mainland, which is the case here, it's connected to the Scandinavian interconnection. So in frequency, it's connected to Scandinavia, but by a single cable, and the cable is often cut because when it's not Russian submarines, it's boats of all kinds, because the sea here is shallow, and so the cut is not very reliable. There are frequent cuts, and when it's cut, the island is truly islanded and has not enough power. Plus, much of the power comes from wind generation. Here is an example of the power generated by wind. You see the peak is 30 megawatt, but this 30 megawatt happens for relatively short amounts of time. The average is perhaps 1/6 of the peak here. So a very high peak to average ratio. So I've deployed all the systems that I've mentioned here with a demand response on all types of systems, and they claim that they can obtain with that 3 megawatts of fast response, which says them they have a generator, diesel generators. They can cut one diesel generator of 3 megawatt using such a demand response here. We mentioned here just the power imbalance due to the lack of production capability or the stochasticity of capability. In the case of Norway, there was another motivation, which was that the grid is weak. Well, this is going to happen in the future more and more, even in countries like Switzerland, when we start to deploy large loads that are, for example, the electric cars. I mean, all of us who have cars, if we replace it by an electric car, that will, depending on how it's done, which car we use, etc. But the evaluations indicate an increase of 30% of the electricity consumption due to electric cars. There's also heat pumps that are also increasing it. This might cause problems to the distribution grids. We've seen such a problem of distribution grid with PVs in the labs. That was one of the motivations, and I've mentioned that already. So that it can happen with PVs. It can happen also with large demands like electric cars. So studies have been done in various countries. That's a study from Belgium that's showing that depending on the penetration of electric car in a given neighborhood, there's a fraction of the electric distribution grid in the city that has been studied, like that has line problems. So essentially, the ampacity of the lines is violated. If everybody starts charging their car with high power chargers, and depending on how the grid is done, if you're unlucky, then that will not work. It will not work, so there will be voltage or ampacity problems that will break some circuit somewhere. So you need somehow to control. So many electric car chargers are actuatable. You can control them if you receive a signal from the grid. That's an example. And that's the idea, is to do this exactly so that you can, instead of doing that type of charging, you perhaps postpone the charging. So that's an obvious candidate for demand response that will take place in the future. So the car chargers that we have today are able to do this, and operators will do that. Now let me conclude with a small, or not conclude, but go on with a small question here. If we look at some of the reports on the development of this, I will mention one in a few minutes, but they are related to one question here. For example, Voltalis doesn't pay nor charge anything to consumers, but claims that consumers benefit by seeing a reduced electricity bill here. Do you think that this is true? Remember, what Voltalis does is send a signal to your blue pods to disconnect your electrical heating systems whenever they find it good for them, because they've sold this as a service to Swissgrid. I close the poll in a few seconds. And the result is a short majority says A, there must be a reduction, and a large minority says B. Well, we will see. I'll leave the response to, we'll see in 10 minutes what is the true answer. There was a study that has been done by the agency in France that's responsible for monitoring such systems, and we will see what is the answer and why. But before that, we need to do a small element of theory. That's the theory that's behind all of the things that we discuss here. It's called the economic theory of demand and supply, which, as you will see, is very basic. And surprisingly, this is what governs the electricity markets today. This economic theory assumes that there is something that's completely mythical, but that's assumed to be happening. It's called the utility. So if I receive some quantity of electricity, say during 1 minute, I assume that I'm able to compute or to express the utility of receiving this. For example, in this room, we need some power to supply the lights and the beamer and this computer. If we receive less than this, it doesn't work, so utility is 0. If we receive more, then there's also not more utility. We don't need more than that. That's all that we need. Perhaps there's a small variability. If we receive a bit more, perhaps there is a small, we could play with the light. We can put a little less or more of the light, but assume there's only one switch here. We have light or not. That's what is called an inflexible load, a non-elastic load. It requires some amount of power to work. If it doesn't have this power, it doesn't work. And if you get more, there's no meaning, there's no sense giving more because it doesn't need more. That's non-elastic load. If you have elastic loads, things that can adapt very elastically, for example, if you are happy, if every light bulb could be controlled independently, then I could say if I have more light, I'm more happy, but if things are bad, we could have less light, and I would force all of you to sit in the same corner where there is some light here. We could have something like this, where we're more happy when we get more, but it's not 0 or 1 here. And typically, this is how things are today. There's a minimum requirement, and then there is some flexibility. That's the model. It's a model. The reality, as we'll see, is a bit more complex, but that's a model. Flexibility comes, for example, from all the things we've discussed. You can switch off your heating system for a few minutes or even a few hours. So if you get less now, you're less happy, but that's not the end of the day. But there's a minimum that you need to let your non-elastic appliances work. That's the demand side. On the supplier side, there is a dual model, which is called the supply curve, which is typically based on this, which assumes that the cost of supply increases, typically in a convex way, quadratic, for example. Here it's not quadratic, shifted quadratic, where in order to provide something, it costs, if you ask me more, I can, but I need to pay more. But there's a limit somewhere. And if I increase more, then the marginal cost increases dramatically. Here's, for example, for typical thermal systems, not thermal, but fuel burning systems, you might have things like this, where if I use more, then the system becomes less efficient. The cost per produced kilowatt is higher, and there's a limit. It goes to infinity at a limit. And if you have a renewable energy, the cost is only in the installation. The production per se has no cost, which means the running cost is 0. As long as you ask me, I can provide you less. I can dump some of the load. For example, if I have a PV converter on the roof, I can ask it to produce less. It comes at no direct cost, because there's a cost, which is the money I don't receive for the electricity that I've thrown away instead of injecting it. But in terms of generation costs, there is 0 cost, an infinite cost of going above. So Q1 is what it can produce, given the insolation or the wind speed and the orientation. And so that's different supply curves here. Then the economic theory is saying that we think that consumers are maximizing utility minus cost. and producers are maximizing revenue minus production cost, which sort of makes sense. But that's because the utility is a bit mythical, but at least for the producer side, and for if the consumer is like a big factory that's using oil or energy to produce something, then they can express that exactly. And therefore, the question is, what should be the market price that is optimal for everyone? Then you see that if at the optimal we cancel the derivative, so the consumer, if the consumer has some flexibility, if the market price is P, the consumer will say, I will buy an amount Q that maximizes my utility minus cost. And if in these theoretical systems, the amount that I will use is such that the derivative, the prime means the derivative of my utility function, at this amount Q is equal to the price P, and vice versa. In the supplier case, the derivative of my cost will be equal to the price. We still don't know what the price is, but whatever the price, if I have autonomously to take a decision, I have to decide how much I will buy or how much I will sell. Given the price, this is what I will do. Now, if we put all of these together, that indicates that what we need is not the utility function, but the derivative of the utility function. That is called the demand curve. So the derivative of the utility function is well defined if the function doesn't have Dirac and things like this, like we had for some of those. And is since the utility is typically concave, the utility function is a decreasing function, and the supply curve is a convex function here. And then the idea is that when everybody goes to market, like happens in the electricity market, it's not you and me who go to market, but the providers of electricity for us, Romand Energy, or if we go and do a dispatch plan for a microgrid here, we go to the market and we have to publish what is called a demand curve and possibly a supply curve if we are a producer. And then the market will balance at a price where both intersect by this economy, the economical theory, because they should be equal here. So this is how things are. And this is how electricity is run in Europe, in continental Europe, and in the US, and in many countries where there's no monopoly. And of course, this is only the market part. So what typically happens is there is a market day ahead, an intraday, and then once the market has closed, the market must close sometime before operation. And then there is a system operator in Switzerland, Swissgrid, that will see whether the market worked. The market works if that happens, if there's supply and the demand curve match. If they don't, then they will intervene and they will ask explicitly to some operators to reduce the supply. For example, they will say, we're sorry, we have a contingency plan, you have to cut by 20%. Or they might ask for some suppliers to increase their supply by forcing some, let me skip this. Back to one example we saw a minute ago, we saw that in Norway, they had this problem with the grid not being large enough. So, and the way they made it possible they solve the problem was by doing demand response in some parts of the country. And then if you look at the paper that reports on that, they show a shift in the demand curve. So that's the demand curve that you had before doing this system here. And the demand curve was crossing the supply curve that generated a given price here. Then you see that that was the original demand here. And the price for a given area of the country was at this high value here. You see that if you shift the demand by reducing demand response has an effect of reducing the demand curve, then the price where they intersect will reduce here. There are other mechanisms that can even reduce it further that we'll skip here. The supply curves are very theoretical for you and me, but they are not theoretical for large consumers. For example, some studies have plotted as a function of the price, the quantity that big industrial consumers would use. Then you see here something that is not exactly a curve, but you could plot a some curve to this here, which is in some sense the supply curve that you have for this part. This is one region in the US, Georgia power here. that has put in place a demand response program. So they have evaluated their curve here and tried to see where the curve would intersect the market, the demand curve, to see how much demand response they need to trigger here. Now that's the theory. The economical theory is just this. There's not more in the economical theory, and this is how markets and electricity is driven in Europe. But there has been many criticism made to this. One that we can easily understand is the pre-bound effect. That's our example that we saw of demand response by price. Here we indicate a high price to incentivize the David's heat pump to not work at the high price. But we see it has a pre-bound effect. Before the high price, we have a large consumption. So that's a side effect, which is not captured by the simple supply and demand curves, but has to be incorporated in the simulation of the system. There has been other papers, I cite one of them here, that criticize this theory by saying that user reaction, when the supply curve is manipulated by user reaction, in fact, it's by people like you and me, and we tend to be binary. We're not smart. We don't adjust by 30%, whatever. We just stop or we don't care. So the response of customers tends to be what is called bang bang. It's independent of the intensity of the price signal. So that, well, those nice intersecting curves are hard to, they don't really reflect what will happen. You need to have a smoother things, which can be done, for example, by TICO and Voltalis. They do that. As you see, they have a zero off control. So the way they modulate it is by modulating the number of customers to which they send the signal, because they sense users are not able to modulate smoothly. But there are other effects that many studies have shown that load shiftings are limited in duration, regardless of the price. Even if the price goes up, after some time, this is a study made in the US. In the US, the problem is air conditioning much more than heating. That the peak is in the summer. You could say, well, that's easy to fix. You install solar power everywhere, solar panels everywhere. That will come, but has not yet come in the US. So they have a electricity provision problem in the summer, and they have demand response programs that send large prices when there's a peak, and then people stop air conditioning, but they stop it for about 90 minutes. After 90 minutes, even if the price is very high, they get so hot and humid that they stop it here. Worse, demand response programs can increase diesel generations or other forms. If you think about it, the business model of TICO is to say, I offer to you, I subscribe by offering to Swissgrid a secondary reserve. That means whenever Swissgrid sends me a signal, increase or decrease, I will do it by some amount that I can calculate by doing simulations like you do in the lab. And they have about 100 megawatts of secondary reserve that they sell. But there is a catch. I mean, heating systems work only in winter, right? In the summer, they can't offer anything. So this, I mean, it's a seasonal business model. TICO doesn't do anything in the summer. Even in the winter, there might be days that are extraordinarily warm in the winter. It happens that it's plus 15 degrees at Christmas. It can be minus 5, but it can be plus 15. So there are still days where there's very little heating, so there is very little you can stop. But since they have a service for helping the grid, even in a hot day, there might still be a problem in the grid, or a warm day where not much heating is done. So they need to provide the service whatever happens. So what they do, TICO, for example, they bought shares in a hydro dam that can modulate power so that they can, if necessary, use the power from their dam if all of the heat pumps are off, for example, and they cannot reduce them. Another more important criticism is that the theory works. It's a theory of abundance. If there's plenty, many generators that are willing to do the job, but some of them are expensive, then the market theory will make sure the expensive ones are used only in the rare moments where they're expensive. But what happens if there's not enough? If there's not enough, well, the market will make the price go to infinity in theory, in practice to a very, very high value. There is still not enough, but the price is very high, which is exactly what happened this winter. It doesn't solve at all the problem. We have the same scarcity as before, as if we did not have variable prices, but we have very high prices, which is very good for producers. I mean, producers of hydropower, for example, could sell the power at 10 times the price they were selling the year before with no difference in their operating costs. That's a criticism that is made of this. In case of shortage, very high market prices can result that are socially unacceptable. Even worse, if you give complete freedom to capitalism, all bad things will happen. So what happened 20 years ago in California, where they introduced this theory of demand response and market and supply and everything, for many things, California is in advance for the good and the bad. Well, a major operator manipulated the market by creating artificial shortages, which had the prices skyrocket and created huge revenues for them. I mean, after all, you pretend there is a failure on a large generator. It's not true, but you disconnect the large generator. The prices become very expensive, and all your other generators will produce at very high prices. Of course, this has been found. The company went bankrupt. The company that did this was Enron. It did a number of other things, other bad things, but they manipulated the prices to get them to a factor of 20, completely artificially, without any shortage. So that's one of the problems here. So let me skip all of this and conclude with a last quiz. So someone asked, was all of this verified? I mean, what happens to all of this? So as far as I know, in France it was done, and probably in many other countries. So this agency has evaluated what Voltalis is doing to the system, and they found two things. On heating systems, it reduces the consumption by about 10%. And on hot water boilers, it had no impact on the consumption. So that's back to the question, does demand response also, beyond shifting the load, displace it in time, does it also reduce? Well, the answer is yes for heating, no for boilers. How do you interpret this? Well, we didn't see the model, but you can perhaps choose one of the other questions. Closing the poll in a second. Closing now. Majority says B. Boiler leakage is small, house leakage is not. That's probably the correct answer. What is happening here is if you stop heating your house for an hour, what will happen is after, when you heat again, of course, during 1 hour, you reduce consumption. But after that, you use more. And since the house is colder, you need more to bring it back to temperature. So is the balance positive or negative? Do you still save by doing it? And the answer is yes, if your house is not so well insulated. Because in fact, during the periods where your house is cold, it leaks less. All the heat you will put into your house after the 1 hour stop is, if you do the calculation, which is given in the slides, the integral of this heat, if it's perfectly insulated, is the same heat you would have put before. So there is no, you just put it differently. But if you look at the equations, you just differ, is the same. If it's perfectly insulated, it's the same, so there's no difference. If it is not so well insulated, well, in fact, you leak less when you're cold because the leak is proportional to the difference in temperature. So when your house is cold, you lose less of the inside temperature, and thus it is this effect here. Of course, it's at the expense of comfort. Voila, that's the end of this module. That's the end of this lecture. It's also the last lecture of the course because next week is a holiday in Switzerland. So there is no lecture. That's why we did it a bit compressed today. But the lab continues. So it's the last lecture of this course. It's also my last lecture because I'm retiring this summer. So that's my last lecture at all. I was so happy to give it to you. But we will meet again. We have the quiz, the lab, and the exam. About the exam, there were some questions. I think I have one slide about this. No document is allowed for the exam, but there is what is called an exam booklet. The version of last year is already online. That will be the same as last year, but with a few perhaps typo corrections. So no document, everything in the head, except perhaps a few formulas that are too complicated to learn by heart, and that are in the exam booklet here. Everything that's not in the exam booklet will not be, you will not have documents here. And we will post the exams of the past 2 years very, very soon.
When will the exam booklet be updated for this year's exam?
This week. Voilà, thank you very much. Thank you.